Hello everyone. In this video we're going to begin a new chapter. So we remain still within the realms of general principles or general performance theory, but we'll continue with the cruise stage of the flight. So we have in the previous video finished with the climb lessons, and we're going to be talking about the cruise. So this is our area of interest for the future. So the cruise is interesting because commercial transport airplanes spend the majority of of their time in the cruise in straight and level flight condition, right? So this is why we must examine the properties of the cruise and why we must find out what the different functions are that described the cruise. And just a little bit of heads up. So what is most interesting to us during the cruise? So during the cruise condition, we have two main questions, like how far can we get? And for how long can we stay in the air? Right, so just as general questions, right? So how far can we get? This might be like a legit question from the management of a commercial air transport company, so one like Wizz Air, where the management would ask, with this aeroplane, how far can we get? Because, this is how we can specify the bases, the destinations, and everything else. And this is how we can specify, for example, alternate aerodromes should the weather go bad, right? How far is the alternate aerodrome, for example, from our airport? Or to give you more an example from the not so distant future, when we will be planning the cross-country flights during your general aviation training phase, we will go to airports which are, a bit further. And this is when we'll have the question like how far can we get with this given aeroplane? And also, for example, we have a given amount of fuel in the airplane in your initial training, and we're doing visual circuits. We have 10 US gallons in each tank. How long is that enough for? How long flying time is that going to give us, right? So these are the two questions. Or when, for example, a commercial air transport airplane goes into what is known as a holding over the aerodrome, because, for example, the weather is bad, and the crew is waiting for the weather to get better at their destination. You might get the question like, how long can we stay in this holding? How long can we stay here, based on the fuel that we have, right? And the answers will be given by the so-called range. The range will answer to us how far can we get from a given amount of fuel, and the endurance is going to tell us how long we can stay in the air from a given amount of fuel, right? But before we go on and examine the range and the endurance, let's look at the forces acting on the airplane in a cruise flight condition. So during cruising, we're going to assume, as we have already seen, a straight and level, unaccelerated, steady state condition. So straight meaning laterally, the aircraft's direction is not changing, so the aircraft is basically flying straight ahead, and level, meaning that the bank is zero, that the aircrafts are unbanked, the aircraft is level, it's not turning, basically. and the change in altitude is 0 as well, right? So this is what we would call a steady state, straight and level cruising flight condition. So during the cruise, we're gonna have, or most of the times we said we're gonna have like 4 major forces acting on the airplane, which are gonna be, of course, the lift, the drag, so the aerodynamic forces, the weight, which is the internal force given by the acceleration of the gravitational field and the mass of the aircraft, and of course the thrust given by the engine. And just one little bit of detour here, because we assume that when we examine the steady state flight conditions that all of these forces acted in the center of gravity. But just as a very quick recap, so if I have a center of gravity, and I have a given force, like this F force, which is acting to a kf distance from the center of gravity, right? Along a given body, and this can be like a general body, like a potato, you know. So so this is the body. In our case would be an aeroplane, but this is a general example. So what we can do is we can transfer this force into the center of gravity of the body. We can transfer this force into the center of gravity like so. But in this case, we're neglecting something. So something else needs to be added before we can do this. So if this force isn't acting in the center of gravity but has an arm to it, it's also going to have what is known as a moment around the center of gravity. And we can see that on this arm, this force is going to be rotating the body around the center of gravity in this manner. So in a counterclockwise direction, and the moment generated by this F force would be the kf arm times the force, right? So the arm times the force equals the moment, and this is the effect it has on the center of gravity. But in reality, just in itself, this force and this arm is going to give us this moment. So we don't explicitly say that this moment is there, because in that case we would count the moment twice, right? So in itself, like this, already this force is generating a moment around the center of gravity with that arm, which would be rotating this body around the center of gravity in a counterclockwise way. So now we put the force into the center of gravity and there is no arm. So therefore, if we just simply did this simplification, we would neglect the turning of the body in a counterclockwise way around the center of gravity. So what we need to do is we need to add this moment to this whole picture, this moment generated by the F force on the KF arm, right? And in this case, we transferred everything into the center of gravity. So here we have the force, and we also have the moment added to the center of gravity. And now we have the same effect, because this force, the sum of the forces is unchanged, so it's the same, and it's acting in vectorially the same direction, so it's the same vector. The sum of the forces is unchanged. So the sum of the forces is unchanged, it is the same, and the tendency of the body to rotate around the center of gravity in a counterclockwise direction because of the mass is still present. So we can do this simplification. So we can always move a force from one place to the other, but we also need to add, in that case, the effect of the arm basically around the center of gravity. So the moment, the effect of the moment which it would have on the given point. So that's the point. Okay, so after finishing with this recap, let's continue to our actual drawing. So here we're going to have center of gravity of the aircraft. We have the longitudinal axis, the vertical axis, and here we're going to have the airplane, right. So we're going to have a wing, and we're going to have an engine. Okay. And also, very important, a stabilizer. Okay. So, and also we will presume the gravitational acceleration to be acting, if this is x, y, and z direction, so 0 and y is 0 and plus g direction, like this. Okay, so in that case, if the body has a given mass, the first force which acts on the aircraft in the center of gravity is of course the weight of the airplane, and if the aircraft flies in a relative airflow, in that case, so it's minus v 0, 0, and we presume this relative airflow to be coming from the negative longitudinal direction. In that case, we're also going to have aerodynamic forces on the wing, right? And just like we have the center of gravity, where we presume the entire mass of the body to be concentrated in, and where the resultant weight of the aircraft, the entire weight of the aircraft to be acting through, as you remember, we also have for the aeroplanes the center of pressure. So here you have the center of pressure, CP, this one. And in the center of pressure, we have the lift force, which is perpendicular to the direction of the relative airflow. And also we have the drag, right, which is parallel with the direction of the relative airflow. And also we're going to have the thrust force, which is going to act in the center of thrust along the axis of symmetry of the engine. Okay, so as you can see, in reality, the forces on the aircraft are not going to look like the simplified drawing, again, like we had initially, where we said that the center of gravity, so here you have center of gravity, and you have the lift, drag, thrust, and the weight of the aircraft acting alone, right? So it's not that simple of a case. In reality, we can presume these forces to be acting in different points. So therefore, we can simplify by moving the forces or dislocating the forces into the center of gravity, but in that case, we need to take the moment that they generate into account. So we're going to have the lift act through a KL arm around the center of gravity. And so what that will generate if you want to move it into the center of gravity, the lift force, is going to generate for us around the center of gravity a counterclockwise moment. So like this one, right? So let's say ML is going to be equal to the KL, so the arm times the lift force. And what we call in this coordinate system, so around the lateral axis, the moments, if the direction is a counterclockwise one, we're going to say that it's a positive pitch or a pitch down moment. Pitch down, sometimes they use nose down, but pitch down is the more correct term. And usually this is what we call a positive moment. So a pitch down moment. So we can see that in this drawing, the drag force is going to have a KD arm from the center of gravity, which is going to generate essentially a moment around the center of gravity, which is going to be, again, a counterclockwise moment. And you can calculate it with the arm of the drag force times the drag force, right? So this is also a pitch down moment. So weight, of course, since it's going through the center of gravity, the arm is 0, so therefore it has no moment around the center of gravity. However, you can see, since the engine is down here, we're gonna have a KT arm around the center of gravity. So it's gonna be generating a moment which is clockwise, and the magnitude you can calculate with multiplying the arm between the thrust force or the axis in which the thrust force is acting and the longitudinal axis times the thrust force. And as you can see, this is a clockwise rotating moment, so this we call a pitch up moment. And this we would call a positive, or sorry, a negative moment. Okay. So, but of course, which moment you call negative and positive is determined on the coordinate system which you use, on the convention basically. So how they index it, for example, is by saying, you know, in this case, well, not xy, so xz, and they would say that this, you know, would be a positive moment, for example, or, you know, this direction would be counted as positive. It doesn't really matter. It's just a question of convention. Okay. So what we get from this entire gameplay is that what we're going to have in the very end is we're going to have a sum of moments, right? And the sum of moments, we could sum them up around the x-axis, sum them up around the y-axis, and sum them up around the z-axis. And of course, these would be the moments acting around the z-axis, right? Because essentially how it looks like, if you want to sketch it up, is that we have the airplane flying in that direction. So here you have the cockpit window, so just that we definitely see in which direction the airplane is going. So here you would have the airplane. Some homeworks are coming in. Okay, so there you have the airplane. And let's say somewhere here you have the center of gravity. And here you would have, of course, the longitudinal axis. So at right angles to that, you would have the y-axis. So this would be perpendicular with this one, and the third one would be pointed towards the belly of the aircraft, which is perpendicular with this one. So this would be the z-axis, and it's also perpendicular with the x-axis, right? And right now we're talking in the about the xz plane, right? So we cut the aircraft in this plane right here, in the xz plane. And we're looking at the moments around the y-axis, right? Because the forces acting in this xz plane generate moments around the y-axis. So around the y-axis, right? I hope that makes sense. So moments in y-axis, or around y-axis. Okay, so we're talking about the moments in the y-axis. So in general case, right now we would presume that this one would be 0, and this one would be 0. So what we're looking at is the sum of the moments in the y direction, and we would see based on the convention. So let's say that we already stated that the counterclockwise moment would be the positive one, in which case let's say you have the moment generated by the lift. You have, with a positive sign, the moment generated by the drag. You have the moment generated by the thrust force with a minus sign, and that's it. And the point is that this not necessarily is equal to 0, right? So this sum of the moments around the lateral axis might not necessarily be 0. And if the sum of the moments is positive in this regard, with this indexation, with the counter clockwise rotation being a positive direction, in that case, if it's the sum of the moments around the y-axis is positive, it means that the final resultant moment is going to be a pitch down moment. So sum of the moments in the y if it's a positive one, and if it's a negative one, with this convention, and again I need to emphasize that this is only true with this convention. So the reason for this is because we presume that the positive moments would be the one which has a counterclockwise rotation around the y-axis, but again, this is up to convention how you wish to view it. Of course, there's positive directions based on the rotations around the axis, but this is how we're gonna presume it for now. Okay, so if it's a negative one, in that case, is going to be a pitch up one. Okay, so because I think in, if I recall correctly, in stability it's quite the other way around, but it doesn't matter, because what we're trying to say is that depending on the prefix and the prefix of the sum of the moments around the center of gravity, the airplane is going to either pitch up or pitch down based on the moments of the sum of the moments around it. And how much is going to pitch up or down is dependent on the magnitude of the sum of the moments. And if these were the only forces acting on an aircraft, in that case, the airplane would just start to pitch up or pitch down uncontrollably, and here the pilots wouldn't be able to control the aircraft around the lateral axis. However, you already learned that the pilot is able to control the aircraft's movement around the lateral axis with the help of the so-called elevator. Right, so with this guy right here. Because what happens if I deflect the elevator, or in this case for commercial airplanes, oftentimes they call it the stabilator, because it's both the stabilizer and the elevator, and the whole thing can be moved. In that case, the resultant force which is going to get generated is going to be in the center of pressure of the stabilizer, is I'm going to generate a force. So in the stabilizer, I'm going to generate a force in the z direction, and I'm going to generate a force in the longitudinal direction. Right? So with this force, in case the sum of the moments given, the sum of the moments of the thrust, the weight, and the drag and the lift is in such a way that the aircraft wants to pitch down, in that case, I would deflect the stabilizer downwards, and what I get from these stabilizer Z force around the center of gravity is on this big arm right here, is this KSZ. It would generate a moment, a pitch up moment around the center of gravity with the magnitude of the arm times the force. And this is what you get from this whole point of view. If you correct just enough, in that case, you can generate the sum of the forces from the around the y-axis, from the lift, weight, drag, and the thrust, plus the moment from the stabilizer in the z direction, and also, since it's also higher than the center of gravity, you're also going to get a moment from the drag or the longitudinal component of the stabilizer force, which is a drag basically, on the KSX arm, which would result again in a pitch up moment. So this would also indicate in this case an MSX moment, which is the KSX arm times the SX force, right? And if we add these together, if the deflection is sufficient, you can generate a situation when the sum is basically zero. The sum is zero, and in that case, the aircraft is in equilibrium. And you can see that it's pretty much determined by one or two critical things. So one, of course, is the position of the engine. That's also going to give us a certain deflection. However, more importantly, the distance between the center of gravity and the center of pressure is also going to influence in which direction I need to deflect the stabilizer, and also the magnitude of the stabilizer deflection angle is going to indicate. Right, so this is what we're going to look at, is that we're going to have like two separate cases based on the position of the center of gravity, of the relative position of the center of gravity relative to the center of pressure. Because what is the center of gravity position dependent on? The center of gravity position of the aircraft, you will learn it from mass and balance. So CG position is usually a function of the initial basic empty mass. So the basic empty mass center of gravity, which is just the initial empty aircraft center of gravity. So that would come down to the mass distribution of the aircraft itself. Like that would be just that. But after that, after the initial basic empty mass center of gravity position, what's gonna affect the center of gravity position is the fuel, where the fuel tanks are located, because there's usually multiple ones and to multiple distance from the center of gravity. How much fuel you load into the aircraft, and to which tank, so which tank positions, and also loading of the aircraft. So loading means like again with the fuel and both with the loading can mean passenger loading and cargo or luggage loading as well. And what it boils down to is how much and where. So what is the magnitude of fuel and loading that you put into the aircraft, and where you put it to basically you cram up all of the luggage to the back of the aircraft, and you put all the people to the back of the aircraft. Of course, that's going to mean that the center of gravity of the aircraft is going to shift forward. But if you put a whole bunch of cargo compared to this initial situation where the center of gravity has shifted rearward, you put a whole bunch of cargo in the front area of the aircraft, then the center of gravity is gonna shift back in, and this is what we mean by this one. Okay, so the center of gravity position is gonna determine how the aircraft gonna act aerodynamically speaking or stability speaking. Where does it want to rotate? So does it want to pitch up or does it want to pitch down? And so that initial tendency is going to determine to which direction I need to move my elevator or stabilator control at the tail of the aircraft, and of course with what magnitude, and that's the question. So we can have usually how it looks like, and you guys will learn this in mass and balance, but just a quick understanding of the whole situation. So in commercial aeroplanes, usually the center of gravity position, because it has such a great effect on stability and control, it is usually limited. And the position is given as a relative percentage to the mean aerodynamic chord of the aircraft. So the center of gravity position would be given as a percentage to the mean aerodynamic chord of the aircraft. And usually there are two limitations to the center of gravity. And here we need to sort of define again something, a convention in aviation of how we say things. So when we talk about moving more into the direction of the longitudinal axis, so in a positive x direction, so for example, you're in the tail of the aircraft and you want to go, forward to maybe the front galley or, the cockpit area, you would go forward, right? So this is what we call, and this is very, straightforward, I think, is when you go towards the nose of the airplane, I would say, or in the positive longitudinal direction, what we say is that you're going forward, or is a forward position of something. But when you're moving, when you're in the cockpit and you want to go, the forward. This would be called in commercial airplanes the forward lavatory, for example. Let's say it's so it's inoperative. It doesn't work, the forward lavatory. So then you would have to go all the way through the cabin to the rearward. But in aviation, we don't say rearward, we say aft. We say aft. And this would be, the aft galley, the aft lavatory. So this is how we differentiate in aviation. So aft is something which is towards the tail of the aircraft in the negative longitudinal direction, and forward, which is more towards the nose of the aircraft. So we don't say like rearward. We do say forward, but we don't say rearward. We say aft. And if we have forward and rearward lavatory, we also have a forward and aft CG position. So this would be the forward CG position, center of gravity, and is given in percentage position or limit, and the aft CG position, and these are limitations. So the aircraft center of gravity during loading cannot be more forward than this position and cannot be more aft than this aft CG position, right? So the center of gravity has to be between these two limiting lines, and both of them are expressed in mean aerodynamic core percentage, so that you can directly calculate whether you're still within the center of gravity position or not, right? Because if you exceed these limitations, the forward and the aft, you could jeopardize the controllability and the stability of the aircraft depending on which limitation you exceed. But again, you guys will learn about this in mass and balance. What we have to look at, however, is the center of gravity's position in relation. So center of gravity position, CG position, relative to the center of pressure. And if the center of gravity is forward of the center of pressure, so here you have the longitudinal axis, here you have the center of gravity, and the center of gravity is forward of the center of pressure, so lift and drag, and there would have the weight. In this case, this would be your center of gravity, or COG. In this case, we're talking about a forward CG position, because the center of gravity is forward of the center of pressure. And if the center of gravity is aft, meaning more rearward of the center of pressure, so here you have the longitudinal axis, you have the center of gravity, CG, and your center of pressure is more forward. So this would be your center of pressure, and here you would have your center of gravity. And if the center of gravity is aft, so rear of the center of pressure, in this case we're talking about an aft CG position. Okay, so let's examine the situation of a forward CG position. So if the CG position is forward, that means that on the on the longitudinal axis of the aircraft, the center of gravity is going to be forward of the center of pressure. So forward CG position. Right, so here you're going to have the center of gravity, and we're going to presume that the center of pressure is on the longitudinal axis as well, so we don't have to deal with the effect of drag so much, because in most cases it's very, very small, its effect. So this would be your center of pressure, right? So around it you would have the silhouette of the airplane. And therefore you would have the wing somewhere around here, right? And also if you have a wing, you also have got an engine, just to make the aircraft complete. Okay, and very important, a stabilizer. Okay, so we also have, before we forget, a vertical axis, and we're going to presume that the gravitational acceleration acts in the vertical direction, solely in the positive direction, so x, y, and z coordinate. Right, so like this. Okay, so in this case, if the aircraft of course has a given mass, and if you have a gravitational acceleration, in that case you're going to have a weight of the aircraft, which is the mass times the gravitational acceleration, and this weight is going to act through the center of gravity in the vertical direction, in this case, right, in the cruising condition. So this would be your weight. Okay. If we have a direction of relative airflow, so in the negative longitudinal direction, in that case we're also going to be generating aerodynamic forces on the on the wing. So we would have a lift, and we will also have a drag force generated. Now I'm not gonna draw them as vectors, because right now we can see that these are, well, one-dimensional vectors, because most of these vectors only apply in the vertical or in the longitudinal axis. So we're not gonna write them up as vectors for simplicity, because in reality these are vector components. Okay. So therefore, theoretically, like we could examine like this one theoretically, if the elevator control is non-deflected, we're going to presume if the elevator is not deflected, so the because this is a symmetrical airfoil, theoretically, the elevator, right? I'm trying to draw it as symmetrical as possible, and if you have the airflow from this direction, so if the camber is zero basically, so it's a non-cambered airfoil. If you don't have a deflection, so if your deflection angle is 0 degrees, in that case theoretically you're not generating well, practically speaking, you're not generating lift, you're only going to be generating drag a little bit, right? The form drag. You're only going to have a little bit of drag, but we're going to assume that in case the deflection angle is 0, this drag is also approximately 0. Okay, so we still have the thrust, center of thrust. We're gonna have thrust right here. It's propelling us forward. Okay, so there you have it, and we already sort of established that that if you want to transfer these forces into the center of gravity, you can do that. However, you need to take their arm into account, right? So in reality, so you would have like this arm right here is the KL, and the moment which the lift generates in this case is a pitch down moment, right? And if you have the moment generated by the thrust on this arm, so KT, you would have the moment generated by the thrust to be a pitch up moment. So because in reality, well, if you just look at this drawing, you could say that theoretically it's possible that at one point with the amount of thrust you could counteract the amount of lift generated and therefore equalize the moments, which is true for a point. And it's also true that you can regain some elevator control or control of rolling around the lateral axis with the thrust. And in case you may have seen Seconds from Disaster, or might have read some books about aircraft crash investigation, you know about at least 2 cases when pilots lost their elevator control. And in that case, the only way they could alter their pitching moment was by altering the thrust, right? Because it's visible that if you change the thrust, the pitch up moment is going to change. And if the center of pressure is not too far to the back, this could actually make the aircraft controllable to some extent, right? But we're not going to presume that, so we're going to presume a fairly healthy aircraft. So in that case, we can see that it's possible that at some point the moment generated by the thrust, the pitch up moment, is going to counteract the pitch down moment which is generated by the lift. And in that case, the sum of the moments around the y-axis is going to be 0. In that case, we don't need any stabilator or elevator deflection. However, if you were to move the center of pressure more aft, which means that, for example, you would put it, the center of pressure would move more to the aft, and it reduces a little bit. However, because your arm got longer, this moment generated by the lift is going to get larger, and you can only give the engines a given amount of thrust, right? So there's going to be a case when the center of pressure moves so much aft, or maybe the center of gravity moves so much forward. It could also be the scenario in which case the thrust is no longer able to counteract the pitch up moment of the the pitch down moment of the moment, or the force, the moment which was generated by the lift, right? So in that case, you will have to deflect the elevator to regain control of the aircraft, to bring the sum of the moments back to zero. So if your pitch down moment is stronger than the pitch up moment, what can you do in that scenario to regain control? You need to generate such a force which would generate, so this would be your center of pressure on the stabilizer. You need to generate in this center of pressure on the stabilizer such a force which would generate a pitch up moment, right? So definitely your force generated would have to point in this direction, right? So the stabilizer, let's say Z force, right? Because this force on this arm, so this arm, this KSZ, generates a moment which is a pitch up moment, right? So the KSZ times the SZ. So it generates a pitch up moment. So to which direction would you have to deflect the elevator, if the relative airflow is coming from this direction, to get such a force? You would have to deflect it, of course, downward. Right, because it deflects the stream of airflow in this direction, so therefore your resultant force would be pointing in this direction. Your resultant force would be pointing in this direction, and the two components, one would be the, as we have already drawn up, the Z component of the stabilizer force, and we're also going to have an X component to the stabilizer force, which is basically the drag generated on the stabilizer. And this drag, or X component on this arm, this KSX, is also giving us a pitch up moment, right? It's also giving us a pitch up moment. So it's helping the Z component of the force. So both components are actually helping to generate this pitch up moment, basically. But of course, the effect of the Z component is much stronger because the arm is much bigger, and usually this component of the two forces is usually bigger as well. Right, so we can see that this is going to be the final picture. So let's just let me just make you guys a little bit clearer picture of what kind of forces we have acting, so that you can see it clear, because there's a whole bunch of things on the drawing now and it might not be completely clear on what we're looking at. Okay, so here we have the airplane. And to just collect the forces which are acting on it. It's not the most beautiful airplane I have ever drawn. My excuses for that. Okay, so we had the weight. Here we had the center of pressure, so we had the lift. We had the drag, and we had the in the center of pressure of the stabilizer up here, we had the stabilizer force. It was deflected downwards, right? So it was deflected downwards. So therefore, the S force generated, the stabilizer force, was pointing downward, and you also had an SX, which was the drag basically of the aerodynamic forces, or the drag component of the resultant aerodynamic forces generated on the stabilizer. And we also shouldn't forget about the thrust force. Okay, so this is a little bit of like clearer image of what's going on with the forces. Right, so let's try and sum up the forces in all directions, right? So we're gonna sum up the forces in the x and z direction, just like we usually do. Because if you remember, that's how we got usually to the conclusion of the final equation. So sum of the forces in all directions, because this is a vector, so sum of forces in x, sum of forces in y, and sum of forces in the z direction. And we're getting the homeworks done. Good. So in the y component is going to be 0, of course, because we only presumed to be looking at the xz plane. So let's start collecting the sum of the forces in the x direction. Okay, so in the longitudinal direction, we have the thrust, we have the minus drag, and we have minus sx. I forget the x from here. Right. Okay. And this has to be 0. Okay, so sum of the forces in the z direction would be equal to the weight plus like the stabilizer force in the z direction is gonna be added to the weight minus the lift has to equal. And this gets us to two equations, is that the thrust has to equal the drag plus the stabilizer force, the drag component of the stabilizer force, and the lift has to equal the weight plus the stabilizer force in the z direction. And so what you can see is that both of these components got added to the initial picture, right? Because initially we said, if everything was to the center of gravity and no stabilizer deflection needed, we just simply said that the lift was equal to the weight and the thrust was equal to the drag, and that was all. And now we see in reality that the stabilizer force cannot be neglected if you want to examine basically the effects on the long-term cruising state. So what this means altogether is that your thrust has to be higher, right? So if your thrust is higher, in that case you're going to have a more pitch up moment, which can reduce the deflection, but only up to a point. But what's more interesting is that your lift has to counteract a higher force, right? So your lift has to be higher than the initial lift. So lift has to be higher than the weight to compensate for this component. And therefore, if lift has to increase, in that case, so if lift has to increase, in that case, your velocity, your true airspeed will increase, in which case, or either the CL is going to increase. In both scenarios, what's going to happen is that your drag is going to increase as well, this component. And in that case, your drag is also going to increase, and that's going to require a higher thrust, right? It's going to require a higher thrust, so therefore more fuel consumption. Because you're also not just carrying the weight, but you're also carrying this weight-like force component, and basically and basically you need to generate more lift, and to generate it has basically the effect of adding more mass to the airplane, and this is also called the apparent weight. The apparent weight, because it has the effect that the same effect if you talk about it aerodynamically or from stability and controllability point of view is that the aircraft increases mass. So it's also therefore going to increase its stall speed, right? Because in the stall speed you have initially like the weight times the load factor, but in this case this gets added to the weight of the aircraft, and therefore your stall speed will also be increased. But that's not the point we're examining. You're going to talk about it quite thoroughly in Principles of Flight. The point that we're examining is that because of this effect, your fuel consumption is going to increase. So yet again, because your lift has to compensate a larger component, so the weight plus this apparent weight, so the Z component of the or the vertical component of the stabilizer force in case of a downward deflection, so in case of a forward center of gravity position, in which case you have the lift formula. So how can you increase the lift? So you either increase your angle of attack, with which you increase your lift coefficient, or you increase the speed. So in both cases, if that happens, sorry, the other way around. So here we increase the speed, and here we increase the lift coefficient. In both cases, you're going to increase the drag, right? Why? Because you have the drag coefficient times the true airspeed squared times the surface area, right? So if you increase the true airspeed, that's quite apparent, that's visible in the formula itself. However, if you increase the lift coefficient, what you also increase is the induced drag coefficient, right? Because it has the square of the lift coefficient in it over pi times the aspect ratio, which gets added all together to this drag coefficient. And also, if you look at the polar curve of the aircraft, it's very visible that because of this effect, if you increase the lift coefficient, your drag coefficient altogether is also going to increase. So therefore, you're generating more drag, which you can only compensate. So if you're generating more drag, you're also going to need more thrust to compensate that, because this whole thing has to equal 0. And this is the final verdict in this case. So altogether, because of this larger thrust, this larger fuel consumption, we're going to see that altogether a forward CG position, so when the center of gravity is forward of the center of pressure, is going to lead to, because of the downward force generated on the stabilizer, which acts like an extra mass on the aircraft, it's going to lead to an increased range, or sorry, quite the opposite. So it's going to lead to a decreased range, larger fuel consumption, and shorter endurance. And if you look at another interesting effect, we can see that on the stabilizer control, on the trim control, what we can see is that the arm of this KSZ, so the arm of the actual elevator control, is going to get longer. So the hinge moment, this MSZ, is going to get larger. So therefore, the aircraft is going to be have a larger hinge moment, a larger stick force is what we call it. So with the forward CG position, we're also going to have a larger or increased stick force. And also the aircraft is going to be more stable if you look at it. You'll learn about this in stability, but if you have basically an updraft which is trying to increase the angle of attack of the aircraft, the initial moment, if you increase the lift force right here, because if you have an updraft, which is going to increase the angle of attack. It's going to increase the angle of attack. Sorry, it's going to increase the angle of attack. It means that the lift force is going to get larger, and this larger, basically lift force, is going to create a larger nose down or pitch down moment. So the disturbance, the updraft, wants to pitch the aircraft up. However, the aircraft wants to pitch down by itself, right? And you guys remember we talked about stability just a little bit, just as a general introduction to like basic stability of what systems we deem stable, unstable, and neutral. And here you can see that in this state, the aircraft to a disturbance, the initial tendency of the aircraft would be to try and generate a motion against this disturbance tendency, right? So it wants to go back to its initial state. So therefore, this CG position would be what we call is more stable. And we call this larger stick force. We call this less controllable. And again, about this, you guys will learn the principles of flight in more detail. So what happens if we have an aft CG position? Let's examine that. What happens if you have an aft CG position? In that case, yet again, we're going to have longitudinal axis. We're going to have center of gravity, and we're going to have the Z axis. So we have the CG, and we're going to have the center of pressure forward of the center of gravity, because the center of gravity is aft of the center of pressure. So this would be your center of pressure. So you would have your wing somewhere around here. You would have your wing somewhere around here. The aircraft generally would be something like this. Will look something like this. Okay, and you would have the stabilizer right here. So we're not going to go into the same amount of detail as we did with the previous one. So let's just quickly draw up the forces. Of course, the aircraft has a given amount of mass. You have a gravitational acceleration, which acts in the positive Z direction. And also you have a relative airflow in the negative longitudinal direction. Okay, so therefore you're going to have a weight of the aircraft, which doesn't generate any moments around the center of gravity. You're also going to have in the axis of symmetry, or through the axis of symmetry, thrust force, things with the center of thrust. And we're going to have a lift, of course, perpendicular to the relative airflow, and we're also going to have a drag force. Okay, so these are all the forces that we need. Out of all of this, the only to generating a moment. At this moment is the lift on this arm, right? So this KL arm, and the thrust on this KT arm. And as you can see, the thrust, because of its position, is still generating a pitch up moment, and the lift is also now generating a pitch up moment. In the previous case, as you remember, the lift was generating a pitch down moment, right? So you can see here the lift was definitely generating a pitch down moment around the center of gravity, and now it's going to generate a pitch up moment. So if I want to bring the sum of the moments to 0, in that case, definitely I will need to generate a force in the center of pressure of the stabilizer, which generates a nose down moment, right? So how do I generate a nose down moment on this stabilizer? So I will definitely need to point my force in the stabilizer upwards, right? So in the negative vertical direction, because this force is going to generate for me a pitch down moment, right? So this SZ, and also I'm going to have an SX. Okay, so where do I need to deflect my stabilizer if I want to generate such a force? Of course, it's just like the wing. I need to deflect it upward. To generate this force. And so therefore, the SZ force on this reduced arm, just remember in the previous case this arm was like pretty large, and now it's much smaller. And also I have this SX arm. So I'm going to have a pitch down moment generated by the SZ, which is going to be equal to the KSZ times the SZ. But also a pitch up moment from the SX. So MSX would be the KSX times the SX. Right, so arm times the force. So interesting, I still have to defeat the drag which was generated by the trim drag is what we call it actually. So this would be the trim drag, or the longitudinal component of the stabilizer force. Right, so the only force pretty much this picture which is generating for me a pitch down moment is this elevator force, interestingly. So in that case, what I can do is write up the sum of the forces, right? So let's presume that I have achieved this. So with this elevator deflection, I have achieved the situation where the sum of the moments is 0, basically. Okay, so let's collect the sum of the forces. I have in the Y and in the Z direction. Okay, so in the X component, or sorry, in the Y component is going to be definitely 0. Let's collect the forces in the X component. So so I have in the longitudinal direction, I have the thrust. I have the thrust acting in the positive direction. I have minus the drag, and I have minus the stabilizer force in the longitudinal direction, and this has to equal 0, right? In the sum of the forces in the Z direction, I see that I have in the positive direction the weight, in the negative direction the lift, and also in the negative direction I have the stabilizer forces component, vertical component basically. And this also has to equal 0. So what I get if I express thrust and lift from these two equations. So from the first one I get that the thrust is equal to the drag plus the trim drag. So that's nothing new. It's just like in the previous case. However, in the second one I get is that the lift is going to be equal to the weight minus the trim force. And this is interesting, right? Because in this case, from the initial condition where the lift was equal to the weight, actually the lift is going to be less than the weight. The lift is going to be less than the weight. And in that case, I can go ahead and reduce the lift. And how I can do that, if you look at the formula, is I can, just like in the previous case, I can reduce the velocity or I can reduce the lift coefficient, right? So I either reduce the lift coefficient or reduce the true airspeed, or I can do both. And in that case, what I'm going to see is that because I have the drag calculated as the drag coefficient times the dynamic pressure times the surface area. Of course, if I reduce the true airspeed and or if I reduce the lift coefficient, I'm going to reduce the induced drag coefficient. So therefore, altogether, the drag coefficient is going to decrease as well. In which case, I can see that the drag is also going to decrease, right? So if the drag decreases on this picture, if the drag decreases, in that case, the thrust can decrease as well. In which case, the fuel consumption altogether decreases. So this would be the effect of an aft CG position. Aft CG position is that your fuel consumption is gonna decrease, so therefore your range is gonna increase, your endurance is gonna increase, and these are the interesting parts for us. And I would like to highlight in the previous case that again, what we need to sort of remember from here, from performance, is these parts, right? Because these ones you learn in principles of flight in more detail, right? But we can go ahead and look at the same two effects as we discussed before, like controllability and stability. And what we're going to see is that in contrast to the previous case, like even if you have the same amount of force, the arm decreased basically. So if the arm decreased, the moment decreased, and therefore the stick force decreased. So the aircraft becomes more maneuverable, more controllable, right? So the aircraft becomes, so controllability increases, which would be beneficial, for example, for very high controllability is going to be usually used for aerobatic aircraft or fighter aircraft. However, stability decreases, right? Because if I have an updraft, like we had in the previous case, which increases the angle of attack, which increases the lift coefficient, in that case, the lift is going to increase, right? And if the lift increases, in that case, actually, it's also the effect that the center of pressure is going to actually move forward. And the lift increases, which generates an even larger pitch up moment. So the initial tendency was to pitch up, and the aircraft wants to pitch up even further in the direction of the disturbance. So what that means from stability point of view is that the aircraft is unstable, because to a disturbance it's responding to an even further tendency of moving towards the disturbance direction. So we will say that the aircraft is, so the stability is gonna reduce. And you can see that in the previous case, stability increased and controllability or maneuverability decreased. And you will see in stability that these two things are against each other. So usually when an aircraft is very maneuverable, is very unstable. So it's very unstable. It's very much maneuverable because it is unstable. And when the aircraft is very stable, it's less maneuverable, because maneuverability is basically moving the aircraft outside of its stable condition. And usually this is why I see that aircraft which need to be from the use or the nature of their use very maneuverable, for example fighter jets or aerobatic aircraft, are usually very maneuverable. However, they're not very stable. So in case of some very modern fighter jets, usually they're so unstable that if they didn't have control computers which helps the pilot give the sensation that he or she is flying an actually stable aircraft, and continuously making adjustments on the controls to get it under a stable condition, in that case the aircraft will be very, very difficult to control. But on the other hand, for example, commercial airplanes or school airplanes in general aviation are usually of a more stable nature, and therefore they're going to be more difficult to maneuver. So this is why you don't see, for example, A320s and 737s or even Piper 28s doing major aerobatic maneuvers. So they're not going to be able to do the maneuvers the fighter planes do. However, it has more stability. So the fighter and the fighter jets and the aerobatic aircraft are more maneuverable, however, at the expense of stability. And however, what's even more important for us from performance point of view is that if you have a forward center of gravity position, like here, so the center of gravity position is forward of the center of pressure, what that's going to mean is that we're going to have an apparent weight. So it's going to increase, it's going to have the effect of increasing the mass, increasing the weight of the aircraft. So the aircraft has to carry more weight. So therefore the thrust, so there's going to be more drag. And so therefore the thrust needs to be increased. So the fuel consumption gets larger. And because the fuel consumption gets larger, this is why you have the decreased range and the shorter endurance, right? Because if you have a given amount of fuel on board, and you burn more, of course your range is going to decrease and your endurance is going to decrease. And this is what we need to remember right here. And the contrary effect with the aft CG position, because you reduce the amount of force which the lift has to counteract, therefore your thrust decreases, so the fuel consumption decreases, which leads to the increased range and increased endurance. So from performance point of view, it's more beneficial for commercial airplanes to achieve an aft CG position. So the aft CG position is better for us essentially than the forward CG position. So therefore we can see that an aft CG position from performance point of view is working in our favor, and the forward CG position is working against us, despite being more stable. So before we talk about it any further, we can or we need to address that, of course, you cannot move it completely, rearward, because then there's going to be a point with this rearward movement of the CG where the moment generated, and it's very visible, I think, the moment generated by the stabilizer is not going to be enough. So this poor moment right here is not going to be enough to compensate for all of these pitch up moments, right? So for all of these pitch up moments, and so if you move it further to the back, even at full elevator deflection, the aircraft is gonna start to pitch up, and that's of course not the best case scenario, right? So there's of course going to be, as we discussed in the beginning, an aft CG limit, and of course there's also going to be a forward CG limit. It's also going to be a forward CG limit. So there is an aft CG limit within which we have to keep the center of gravity. So how we can achieve an aft CG position is with the loading of the aircraft, basically. Loading of aircraft, meaning where you put, so how much fuel and passenger. So loading would be passenger and cargo, baggage, how much and where you put them. This is collectively speaking the loading of the aircraft, and also fueling. The same question, like how much fuel you put in the aircraft and where you put it. And in some wide body airplanes, and also, for example, for the Concorde, what they used to do is they would pump the fuel from some tanks which were more forward to the tanks in the tail to basically move the center of gravity position. That is an option. From what I understand, the only amount of flexibility that you have with a medium range transport jet with such as the A320, A321 family is that you use with the fuel management, with which or the fuel in which tanks you use first and which tanks you use later. So usually, from my understanding, they initially use the fuel which is inside of the aircraft's fuselage first, because usually what they have here is a tank in the fuselage and wing tanks, right? And so these wing tanks usually move the center of gravity position, a little bit aft. So first you would use the fuel from the fuselage, and after it's pretty much left, then you would move on to use the fuel from the wing, and that's also helping to reduce the moments of the generated on the wing. But again, you learn about this in aircraft general knowledge and systems, so that is not required now. It's just mentioning that with the loading and the fuel management and planning, you can actually move the center of gravity position. But for the medium range transport jet and for the general aviation, usually it's this activity, I would say, which is more prominent in changing the center of gravity of the aircraft. So loading is the activity which has the most effect on the center of gravity position. One thing which we need to address in this area is the effect of engine position. So it's not only the center of gravity, that's the main thing, However, you saw that usually effective position of engine, or engine position would have been more correct, is that you're gonna see like two main different compositions. So the first one is when the engine, so center of thrust is below center of gravity. And this is the general case, and this is why we looked at that scenario, because in modern day commercial transport airplanes, and especially with the one you guys will be flying, the A320, this is the case, right? Because here you have the center of gravity in the middle, we have the z-axis, so here you have the silhouette of your airplane, you know, somewhere you have the wing, and you have also the engine, and you can see that the symmetry, the axis of symmetry of the engine is below the center of gravity, and therefore the thrust is going to have a pitch up moment around the center of gravity. If you think about it, this is usually a good thing, right? So this is why it's more beneficiary from practical flying perspective, is that when you're taking off, for example, the moment generated by the thrust is helping basically to rotate the aircraft around its lateral axis, so it's helping you to pitch up. Or for example, when you're doing a descent with low thrust setting and you have to go around for some reason, so in that case you initiate a larger power, so that's again going to increase the pitch up moment. So the aircraft is helping you to transition from the low power descent. So here you have center of gravity, you have a low power descent, and then you just add the power. You know, you want to go around because you don't see the runway or there's a problem. You have a problem with the aircraft, you have a center of gravity, and you increase the thrust. You have the longitudinal axis, and this increased thrust is gonna pitch the aircraft up and help you to bring the aircraft into a climb during a go-around. It's actually very beneficiary. So you have center of gravity, you have the engine, you have the large thrust, you have the longitudinal axis, and it's helping you to generate this pitch up moment. So from a lot of point of view, it's actually beneficial. But on the other hand, you have the other construction. So when the center of thrust is above the center of gravity, like a lot of you would say, for example, maybe DC-9, MD-11, but some of those aircraft also have engines on the underneath the wing. So I would think of a modern day construction of the, for example, C-17. So you have the longitudinal axis and the z-axis, and you have the silhouette of the airplane around it. Try to be precise with it. Oh, actually, let's put the center of gravity a little bit lower, because it is usually lower. It's not as high as I drew it. Maybe we can draw the airplane first and then the rest. So here you would have the wing, because it's an upper wing construction, and here you would have the engines, like all four of them. Right, and here you would have the tail of the aircraft. Generally speaking, you know, here's the cargo bay inside of the aircraft, right? So generally speaking, the aircraft center of gravity is usually fairly low. So it would be somewhere here, let's say. And here you have the longitudinal axis of the aircraft. Here you have the vertical axis of the aircraft. And generally speaking, let's say that these two engines are aligned, which they're not in reality, but they're pretty close. So you can see that in this case, the center of thrust for these engines is going to be higher than the center of gravity. In this case, it's quite interesting because if you add more thrust, the moment generated on this KT arm is going to be a pitch down moment. So during takeoff, this is actually going to increase the pressure on the nose wheel, right? And it's going to work against pitching the aircraft up. So it's very interesting. And also during a go around, this would also generate a pitch down moment. Of course, it can be compensated for, and it is compensated for, and pilots are usually, believe it or not, fairly smart people, and they can handle this stuff. It's a very uncommon condition for commercial airplanes. However, the reason I brought this example is that, for example, when the engines are low, the aircraft is more susceptible to what is known as FOD, which is, I just forgot the FO, but basically it's the debris on the ground which can be sucked into the engine, right? So the aprons, the taxiways, the runways have to be very clear. And the second is that, I just remember, this is foreign object damage, FOD, foreign object damage, which is caused by the debris on the ground, for example, or could be, if the engine sucks something up, some debris, it could cause a foreign object damage to the engine. So, these aprons, again, taxiways, runways have to be kept very, very clear. And the second thing, that's a negative side. However, on the positive side, it's much more easy to maintain. So the maintenance is much easier because it's close to the ground. This is why actually on the 737 100 and 200 was developed with this lower wing, low engine consideration, because it was actually much more convenient for maintenance personnel. This one, however, this construction, the reason why you can see it on military airplanes usually and most of the time is that it has the negative side that the maintenance is much more difficult. So maintenance is much more difficult on this one. They need to use outside equipment, harnesses and everything. So it's a very aerobatic maneuver to actually, do maintenance on these kind of engines. However, since they're very far from the ground, so they're much less susceptible to foreign object damage from the debris that is on the ground. And for example, the C-17 or the C-5, you can find videos of it online where it's operating and for example, like desert conditions. So it's taking off and landing on the dirt road basically. And in that case, you just need to have the engines very high so they're not that susceptible to the debris that you can get into the engine. So this is the reason why, despite of its negative effects, they still use this construction, for example, in military transport airplanes. But for, generally speaking, in modern commercial transport airplanes, because of their accumulated positive effect, they use the center of thrust below the CG. So usually they put the engine below the center of gravity. Okay, so that's it for this video. In the next one, we'll be looking at the effect of the maximum straight and level speed during the cruise, and after that we'll continue with the effect of range and the endurance during the cruise. Okay, so thank you for your attention, and I'll see you guys in the next video.